In this last video of this lecture, I want to say something about the proof of Theorem 9. So this is the last big thing that went into the proof of the fundamental theorem of Galois theory that we haven't actually proven yet. So we stated this theorem, and we used it to prove a bunch of important consequences. So that we can say that we really did give a full proof of the fundamental theorem of Galois theory, I want to go back and talk a little bit about the proof of this theorem. So I'll also say that this argument is complicated, and it's not the kind of thing that you would need to know for any exam in Math 206 or for any algebra qualifying exam. I'll also point out that many other algebra sources that talk about Galois theory prove the fundamental theorem of Galois theory, but they don't do it this way. So, for example, most other sources that you might find don't talk about independence of characters. So, for example, if you look at the proof in Conrad's The Galois Correspondence Notes, it doesn't go this way. So most other sources use the primitive element theorem to prove the fundamental theorem of Galois theory. And we haven't proven the primitive element theorem yet. We'll prove it soon, but we could have. We could have done it in the other order where you prove the primitive element theorem first and then use that to prove the fundamental theorem of Galois theory. So even though you won't need to know the details of this argument for exams for this course, I do want to give you a sketch of the big ideas, and I encourage you to look up the details in Dummett and Foote at least once. Okay, so what are we proving? If G is a finite subgroup of the group of automorphisms of a field K, and F is the subfield of K fixed by G, then the degree of K over F is the size of this subgroup G. Okay, so here's a sketch of the proof. We're first going to prove that N, the size of this subgroup, is at most the degree. And we're going to prove this by contradiction. We're going to suppose that N is actually bigger than the degree, which is M. So if the degree of this field extension is M, then there's a basis for K over F of size M, and we can name the elements of that basis, omega 1 up through omega M. So the big idea that goes into this proof is that we're going to use the automorphisms that we have and these basis elements to define a system of equations. And then we'll use facts from linear algebra to say something about solutions to those equations. So this whole thing has a kind of linear algebra feel to it. So what is this system of equations? We have sigma 1 omega 1 times x1 plus sigma 2 omega 1 times x2 plus sigma n times sigma n of omega 1 times xn equals 0. So we have these n variables, x1 up through xn. Omega 1, this first basis element, is fixed all through this equation. Then we have sigma 1 of omega 2 times x1 plus sigma n of omega 2 times xn equals 0, all the way down to sigma 1 of omega m times x1 plus sigma n of omega m times xn equals 0. Okay, so what's important about this system is we have one equation for each omega I, omega 1, omega 2, up to omega m. So we have m equations. And how many unknowns do we have? One for each automorphism, sigma I, so x1, x2, up through xn. So what do we have? We have m equations in n unknowns. And what are we assuming? That n, the number of unknowns, is bigger than the number of equations. So that means this system has a non-trivial solution, beta 1 up through beta n, where these are elements of K. Okay, so what are we going to do with this non-trivial solution, beta 1 up through beta n? We're going to show that this gives a dependence relation among our automorphisms, sigma 1 up through sigma n, that beta 1 times sigma 1 of alpha plus beta n times sigma n of alpha equals 0 for all alpha in K. Well, how would you even start doing this? What do you know about alpha? It's in K, so you can write it as an F linear combination of omega 1 up through omega m in a unique way. So I will leave the details of this argument, this part of it, to you to check. But in the end, what does that give? This contradicts corollary 8, that sigma 1 up through sigma n, these automorphisms, these are supposed to be linearly independent functions of k, of our group, which is k star. But this is giving a dependence relation. So that's the contradiction that proves that n is at most the degree of k over f. Okay, so I'll pause and erase and talk about the other direction, which is more complicated, but uses some of the same ideas. Let's continue our sketch of the proof of Theorem 9. We've shown that n is less than or equal to the degree of k over f by contradiction. And now we're going to prove that n is actually equal to the degree of k over f by contradiction also. So let's suppose that n is less than this degree. So we're going to get a contradiction here. If n is less than this degree, then there are at least n plus 1 elements of k, let's say alpha 1 through alpha n plus 1, that are linearly independent over f. Okay, so we have n plus 1 elements in k that are linearly independent over f. We get a system of equations. Sigma 1 of alpha 1 times x1 plus sigma 1 of alpha 2 times x2 plus sigma 1 of alpha n plus 1 times xn plus 1 equals 0. In this equation, it's the same sigma 1 applied to each one of these n plus 1 elements in k. We have another equation for sigma 2, and then sigma n of alpha 1 times x1 plus sigma n of alpha 2 times x2 plus sigma n of alpha n plus 1 times xn plus 1 equals 0. So what do we have? We have one equation for each one of these automorphisms, sigma I. So we have n equations. How many unknowns do we have? One for each of these alpha i's, n plus 1 unknowns. So more unknowns than we have equations. So we have, for good linear algebra reasons, a non-trivial solution, beta 1 up through beta n. Sorry, beta 1 up through beta n plus 1 in k. So it's important to note that not all of these beta i's are in f. Why not? Well, what is sigma 1? Sigma 1 is the identity on k. So what does this first equation look like? It would just look like alpha 1 x1 plus alpha 2 x2 plus alpha n plus 1 xn plus 1. So if all of the beta i's were in f, then alpha 1 up through alpha n plus 1 would be linearly dependent over f. So what does that mean? That means that not all beta I are in f. So at least one of them is in k, but not in f. And now, one big idea is similar to the proof that we gave for linear independence of characters. There maybe are many different solutions, non-trivial solutions, beta 1 up through beta n plus 1. So among all of these non-trivial solutions, we're going to choose one with the fewest number of non-zero bi's. By renaming the alpha i's if we have to, we can suppose that the non-zero bi's are b1 up through br. Okay, we can also note that if we divide each one of these xi's through by this is a homogeneous linear system of equations. So if we divide each bi through by the same value, we get another system. So we can divide all of the beta i's. Sorry, I keep saying bi, I mean beta I. If we divide all of the beta i's through by beta r, then we can suppose also that beta r equals 1. Okay, so what do we get? So here, I am saying that we're going to get a system that looks like sigma I of alpha 1 times beta 1 plus sigma I of alpha 2 times beta 2 plus sigma I of alpha r minus 1 times beta r minus 1 plus sigma I of alpha r times beta r, which we can suppose is 1, that this is equal to 0. Why do I call this a system? This is one equation, but we have one such equation for each sigma I. So in fact, we have n such equations that look like this. Okay, so what are we going to do with this? Now, we're going to use the fact, not just that these are a bunch of automorphisms of K, not just that they're a bunch of functions, but that they're actually elements of a group. So these are the elements of a group. So if we take each of these elements and we multiply through by any fixed element in this group, we just get a permutation of this set. So sigma 1 up through sigma n is the same as the set sigma k0 sigma 1, sigma k0 sigma 2 up to sigma k0 sigma n. Okay, and now there's something to do. You want to use this in some way along with this system to find a contradiction where we're going to get a solution to this system, a non-trivial solution beta 1 up through beta n plus 1 that has fewer than r non-zero beta i's. So there's definitely something to do here, but I've sketched at least the big inputs that go into the proof. So I recommend that you go through the proof carefully, the one that's given in Dummet and Foote, at least once. But remember, this is not something that you'll need to know for any exam for Math 206 or for the algebra qualifying exam.